Hi, Chris Kuzmal here. Now we're going to be looking at relational analysis, which is lesson 7 from the logic text. And this is commonly the 7th day also in a intensive camp experience where you're spending uh, six hours more or less a day studying the topic. So that's why it says day 7 there. And lesson 7 is actually pretty short. We might even get it done in 5 minutes here. It's a set of diagramming techniques and other ways of simplifying problems. And the order that I'm going to present them are truth tables, Boolean relational tables, enumerated relational tables, and tree-based search, which is not the exact order that you see in lesson 7. A Boolean relational table is one where if we have a binary relation, such as earlier, so A is earlier than B in the alphabet, okay, then is a binary relation, and we can form a two-dimensional table out of it in order to be able to visualize that relation overall. And so here we see really interesting, oh, it looks like I didn't finish making the slide. So let's see if we can fix that real time. I need to get out of the presentation mode, and we'll go in here and we'll change this D row to be all zeros, okay? And it wasn't hard to spot that because I had this relational table here all set up for me to make it so I could just spot that there's this upper triangle here, okay? Now what am I talking about? This upper triangle, all the ones, all the true values are in the upper right-hand corner of this two-dimensional table. And so we can see how a simple thing like a two-dimensional chart can help us visualize the nature of a relation. Of course, we might have an completely unconstrained situation where we have, for example, 4 unary relations with 2 object constants, and we might be forced to create the entire truth table. And that's actually going to be, pretty complex. And it's sometimes it's useful just to know how big your problem is, though. And so a truth table can help. And if you have some kind of constraint on that problem, such as we only have one true value for each relation, that means in the first 4 columns, we're allowed to have at most 1 true value. And in the second 4 columns, we're allowed to have at most 1 true value. And out of those 256 values in the previous table, there's only 16 values that remain, 16 rows that remain, and that makes your analysis much more tractable. So if you can just spot those kinds of constraints in your problem. And if we can take that and view each relation possibility as a number from 1 to 4, we can build a 4x4 table. Those 16 values now are corresponding effectively to, actually this isn't the 16, those are the 16 rows. Each one of those rows then we have to do an evaluation for a particular relational sentence. And so in this case, we have the relational sentence for all x, p of x implies q of x. The question is that true? If we look here, it's a little bit hard to suss that out, but we can build a table like this and very quickly note that p of x implies q of x exactly. When the relations hold, only one of them can be true for each row or column. And so that means that we have to have just the diagonals satisfy the relational sentence.